When an underwater volcano erupted near the small uninhabited island of Hunga Tonga-Hunga Ha'apai in January 2022, two weather satellites were uniquely positioned to observe the height and extent of the plume. Together they managed to capture the highest cloud plume on satellite records. Scientists at NASA's Langley Research Center analyzed data from NOAA's Geostationary Operational Environmental Satellite 17, GOES-17, and the Japan Aerospace Exploration Agency's JAXA, Himawari-8, both of which operate in geostationary orbit and carry very similar imaging instruments. The team calculated that the plume from the volcano's eruption on January 15 increased to 58 kilometers, 36 miles, at its highest point. Volcanic gases, steam and ash reach the mesosphere, the third layer of the atmosphere. Prior to the Tonga eruption, the largest known volcanic plume in the satellite era came from Mount Pinatubo, which spewed ash and aerosols up to 35 kilometers into the air over the Philippines in 1991. The height of the Tonga eruption was 1.5 times its height. From Pinatubo feathers. The intensity of this event far exceeds any storm cloud I have ever studied, said Christopher Bedka, an atmospheric scientist at NASA Langley who specializes in studying extreme storms. We are fortunate that it can be seen well by our latest generation of geostationary satellites, and we can use this data in innovative ways to document its evolution. The animation above shows a stereo view of the Tonga eruption plume rising, evolving, and spreading over 13 hours on January 15, 2022. This animation was created from infrared observations obtained every 10 minutes by GOES-17 and Himawari-8. Based on these observations, the explosion the start quickly rises from sea level to 58 kilometers in about 30 minutes. Soon, the secondary pulse rose to exceed 50 kilometers, then separated into three parts. Typically, atmospheric scientists calculate cloud heights by using infrared instruments to measure cloud temperatures and then comparing them with model simulations of temperature and height. However, this method relies on the assumption that temperatures decrease at higher altitudes. This is true in the troposphere, but not always in the middle and upper layers of the atmosphere. Scientists need a different method to calculate height, geometry. Klepenkov and Bedka used a technique they originally designed to study intense thunderstorms that penetrate the stratosphere. Their algorithm matches simultaneous observations of the same cloud views from two satellites, and then uses stereoscopy to create a three-dimensional profile of the elevated clouds. Klepenkov then verified the stereoscopic measurements using the length of the shadow cast by the highest plume in the vast ash cloud below. They also compared their measurements with analyses of NASA's GEOS-5 model to determine the local heights of the stratosphere and troposphere on that day. The uppermost parts of the plumes immediately sublimate due to the very dry conditions in the mesosphere. However, the mass of ash and gas spread in the stratosphere at an altitude of about 30 kilometers, and eventually covered an area of 157,000 square kilometers, larger than the state of Georgia. When volcanic material rises this high into the stratosphere, where winds are not as strong, volcanic ash, sulfur dioxide, carbon dioxide and water vapor can be carried throughout the Earth, Klepenkov said. Within 2 weeks, a major plume of volcanic material circled the globe, as observed by the Cloud Aerosol Lidar and Independent Pathfinder satellite observation satellites, as well as the Ozone Mapping and Profiler Suite on the Suomi NPP satellite.